In this video, I want to look at vectors and parametric equations of lines and planes. I previously talked about equations of lines and planes that are determined by a point in a normal vector. However, there are other useful ways of specifying lines and planes. As an example, a unique line can be determined by a point on the line and a non-zero vector parallel to the line. A unique plane can be determined by a point in the plane and two noncollinear vectors, v1 and v2, parallel to the plane. As an example, a unique line can be determined by a point on the line and a vector parallel to the line. As an example, if I have this line here, we need a point on the line and then the vector will give us the direction of the line. Similarly, for a plane, we would need a point and two noncollinear vectors parallel to the plane. The best way to visualize this is to take the vector that determines your direction and then think of translating it up so its initial point is at your given point, like I did here in this picture. So let's start by looking at the equation of a line. Let's refer to our point as x0 and our parallel vector as v. Then if x is a general point on the line, the vector x minus x0 will be some scalar multiple of v. So what we know, x minus x0 is equal to tv, or x is equal to x0 plus tv, where t is a variable known as a parameter and can vary any number from negative infinity to infinity. And as t varies between different numbers, our point x is going to trace out the line. The actual theorem tells us that if we have a line L that contains the point x0 and is parallel to my non-zero vector v, then the equation of the line through x0 that is parallel to v is given by x is equal to x0 plus tv. And if x0 is just equal to the 0 vector, then the line passes through the origin. The equation has the form x equal to tv. Next, let's consider a plane. For a plane, we need a point, x0, and we need two noncollinear vectors. We'll call them v1 and v2. In this case, our plane is given by x minus x0 is equal to tv1 plus sv2, where t and s are my parameters. They're going to vary independently from negative infinity to infinity. So as I pick a value for t and a value for s, I'll get a different point x on the plane. Equivalently, we can write this as x equal to x0 plus tv1 plus sv2. Our theorem then states that if w is a plane that contains the point x0 and is parallel to the noncollinear vectors v1 and v2, then the equation of the plane through x0 that's parallel to v1 and v2 is given by the equation x equal to x0 plus tv1 plus sv2. And similarly to lines, if my x0 point is just the 0 vector, then the plane passes through the origin. When we write a line or a plane in these forms that we've been discussing, these are known as vector forms. These are vector forms of the line and the plane. We may want to express it in parametric equations. If the vectors in my vector form equations are expressed in terms of their components and then the corresponding components on each side are equated, this is what parametric equations look like. So let's look at some examples to see how to do this. Let's find vector equation as well as parametric equations of the line that passes through the origin and is parallel to the vector v equal to -2, 3. Well, since it passes through the origin, we know that x0 is just equal to the 0 vector. We also know that lines have the form x equal to tv. So the left-hand side is just xy. The right-hand side, we do t times v, so -2t, 3t. And this right here would be our vector form. We could have also written it as just t times -2, 3. For our parametric form, we would just set corresponding parts equal. X equal to -2t, y equal to 3t. And this would be our parametric equations. Next, let's find a vector equation and parametric equations of the line that passes through the point 1, 2, minus 3 and is parallel to the vector 4, minus 5, 1. Let's start with our vector equation. In this case, we have x0 is 1, 2, minus 3, and v is equal to 4, minus 5, 1. We know the formula is x is equal to x0 plus tv. Well, since we're in 3 space, x is of the form x, y, z. x0 is 1, 2, minus 3. And then we do plus t times v, 4, minus 5, 1. And it's absolutely fine to keep it in this form. For our parametric equations, we start with x, and then we look at the first coordinates. We have 1, and then a 4t from the second parentheses, so 1 plus 4t. Y is the second coordinate, so 2 minus 5t. And then z would be minus 3 plus 1t. So over here we have our parametric equations. Let's use the vector equation that we just found to find 2 points that are on the line and different from 1, 2, minus 3. So here's the vector equation we just found. And the idea is we just need to pick different values of t. Any value of t will give me a different number, or a different point. If I let t be equal to 1, then I have x, y, z is equal to 1, 2, minus 3, plus 4, negative 5, 1. Or 1 plus 4 is 5. 2 plus negative 5 is negative 3, and negative 3 plus 1 is negative 2. So here I have a point that is on the line. If I were to let t be equal to something like negative 1, well, now my point is 1, 2, negative 3, minus 4, negative 5, 1. 1 minus 4 is negative 3. 2 minus negative 5 is 7, and negative 3 minus 1 is negative 4. So here's another point. And any value that you plug in for t will give you a different point on the line. It doesn't have to be a whole number. It could be a fraction or a decimal. It doesn't even have to be rational. It could be something like pi or e. It can also be positive or negative, as we saw here when we use negative 1. Next, I want to find the vector and parametric equations of the plane x minus y plus 2z equal to 5. I'm going to start by finding the parametric equations. And I can do this by just solving for any one of the variables in terms of the other two, and then using those other two variables as a parameter. So as an example, I could take this equation and rewrite it as x is equal to 5 plus y minus 2z. Well then, if I change to parameters, I could have 5 plus a parameter t minus 2 times a parameter s. So there's my equation for x. We just substituted a t for a y, and we substituted s in for z. So my other equations is y equal to t and z equal to s. And so now I have a parametric equation. From there, it can be easy to get a vector equation. Well, the constants, I have a 5 on the x. I have no constant here, no constant here, so 5, 0, 0. I then look at the t's. I have a 1t for x, 1t for y, no t's on z. And then if I look at s, I have a minus 2s for x, no s's for y, and a 1s for z. So here I have my vector equation and my parametric equations.